Welcome to Unit 9, Inference for Quantitative Data, Slopes. This is topic 9.2, confidence intervals for the slope of a regression model. So to build a confidence interval, you really have to have a strong understanding of a sampling distribution for slope. So for a simple random sample of n observations, let B represent the slope of a sample regression line. The sampling distribution for B will therefore model all possible slopes B. So imagine if you're looking at a sample of data and you find your two quantitative variables, x and y. Each individual, you measure x, you measure y, you make a scatter plot, and you create a linear regression line through that data. You're going to get a sample slope. But that's just the sample slope from your sample of n. There's all other samples out there that could produce a whole bunch of other sample slopes. And a sampling distribution will show you all those other possible values. So we want to describe this sampling distribution. So of course we have to define the parameters, the mean and the standard deviation, and of course the shape. So let's talk about the mean real quick. Well, this should make a lot of sense. The mean of the sampling distribution equals the population mean slope. So just like we've seen in the past, we're going to find the mean of all possible sample slopes. Well, the mean of all possible sample slopes should equal the true slope of the entire population, not just your set of points, right? That's your sample slope. We're talking about the slope of the slope of the entire population that you're examining, and we call that beta. So now, of course, this is on the condition that the samples must be drawn randomly to avoid bias. So now, truthfully, we don't know beta, right? The whole point of a confidence interval is we're trying to find out what beta could be. But we first have to realize that we could visualize that in the model, the true slope beta will be in the center. So remember, that's the key detail with the confidence interval is, yeah, you don't know the true population parameter, whether it be a proportion, a mean, or in this case, a slope, but you know that that true population parameter is going to be in the middle. And that's really important when it comes to calculating a confidence interval. All right, so then we also know, by now I hope we know, that samples are naturally going to deviate. So some slopes are going to be a little bit higher than the true slope, and some slopes will maybe be a little bit lower. There's going to be some natural variability that comes when you look at samples. So here is the official formula for the standard deviation of all of the sample slopes. And that's a little bit tricky, which if you remember in the last video, I said you're not going to be expected to actually use this, but I do want to walk through it. So on top is the standard deviation of the true regression line. This is the standard deviation of the population regression line, which, let's be honest, you're never going to really know. Down the denominator, we see our square root of n, as we have seen before, but now we also have to multiply it by the standard deviation of the population of all x values. Well, once again, we're not going to know the standard deviation of the population of all x values. Typically, all we have is our data. Let's just say we have our 12 data points. Well, we're going to have the standard deviation of our regression line. That's S, you might remember that. But we're not going to have the standard deviation of all, the entire population. That's just not going to be found. And then we also have the standard deviation of our x values, right? We have that. We could calculate that. We got our 12x values. We can find the standard deviation, use a calculator. It's pretty easy. But we're never going to know the standard deviation of the population of all x values, so not really feasible to know. So, of course, we've actually seen this happen in the past. Instead of using the standard deviation for the sampling distribution, we're going to use his close friend, the standard error. So the standard error for a sampling distribution is using values that we do know. On top is S. That is the standard deviation of our sample residuals. Remember, we've seen that before. That comes for free in that computer output table. Then we have the standard deviation of our x values, which again, if you have all of your x values, you can easily type that into your calculator and get the standard deviation of just those x values. And then we also have the square root of n minus 1. Now, for reasons beyond the scope of the course, we are going to use n minus 1 here instead of the square root of n, which is what the other formula I showed you has. Don't really worry about y right now. Again, you'll learn more about that if you take stats in college. It's just a little bit beyond the scope of this class. But let's be honest, this is even better news. You're actually never going to need this formula. The standard error of the sampling distribution will always be given to you, right? I have seen multiple AP tests, multiple AP questions, and this number is always going to be given to you. No one is going to be expecting you to calculate this number on your own. Trust me, right? It's going to be given to you. You do need to know how to interpret it, which we're going to talk about later on this video. So again, One more thing, though, is of course, if we're understanding that some samples are going to vary, some are going to be higher, some are going to be lower, we do have to make sure that our samples are independent of each other. And if you're sampling, without replacement, you might violate independence. But as long as we meet that 10% condition that we've been working on for a while now, as long as our sample size is under 10% of the population, we can assume independence. So the key takeaway from here is that this formula is going to be given to you, or the value will be given to you, so you don't really have to do a whole lot of work. All right, and finally, what's the shape of that sampling distribution? Well, you guessed it, it's going to be normal. So let's talk about this. So now, since we are using standard error instead of standard deviation for the sampling distribution, we do have to use a t-model. And remember, t-models come in many, many, many different types, all based on degrees of freedom. The degrees of freedom for a slope sampling distribution is n-2. Why n-2? Because there's two variables, x and y. So that's why it's going to be n-2. Don't worry too much about that. It's pretty easy, though. Instead of subtracting 1, which is what we've seen in the past, it's n-2. All right, now, the condition that allows this to be true, right? Let's kind of walk through it, right? Right smack dab in the middle is going to be the true slope of the entire population. We want to go up, 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 and down, down, down by standard deviations, but again, we're going to use standard error, which is why we got to use a t-model. Just a little shorter and more spread out. No big deal. And the condition that allows for this shape to be normal is that the residuals must be somewhat normal with no major outliers or skewness. So you actually have to take a look at your residuals, which we've talked about way back in Unit 2. Remember, the residuals is each actual y value minus its predicted y value from the regression equation. And you're going to make sure that those residuals have no major outliers, no major skewness. That way we can be normal. Now, honestly, these conditions are a little bit trickier this time. We'll talk more about them, but oftentimes you don't have to worry too much about the conditions here, but we will walk through them. All right, so, why do we need a confidence interval, right? The title of this is finding a confidence interval for the population slope. So the general idea is very simple. We know the slope of the regression line based on our sample. That tells us how we predict y values to change based on an increase of one x value. But what is the slope of the entire population? How do we expect all of the y values to change based on the increase of one value for x for the population, not just my small sample? Well, we don't know. We don't know the true slope. We want to find it, and that is, of course, beta. So we're trying to estimate what beta is. And this is going to be a t-interval. Hopefully you understand why we got to use t, because we're using standard error here. And it's a t-interval for the slope. So an interval is going to have a bottom, it's going to have a top, and we're going to be fairly confident, 99, 95, 98, depending what you're given in the problem, that the true slope is somewhere in that interval, okay? So why are we using t? I just have to say this for the third time now. Remember, it's because when we build that sampling distribution, we have to use standard error because we can't use standard deviation. There's just too many values that we're not going to know from a sample. All right. So here is the basic 4 steps. They're going to sound fairly familiar, and the formula to find a t-interval for the slope of a regression line. So number 1 is name the interval, which we'll go over here in a second. But again, I already said it's a t-interval for slope. Check the conditions necessary for the sampling distribution. There's actually a little bit more conditions here that we will go over in a moment. Number 3 is to build the interval. Now, building the interval is actually really easy. You start off with your slope, the slope you found from your sample. Then you go up and you go down by what is called the margin of error. That's this back part. To find the margin of error, you take t star, which you're going to use on your calculator, invert t to get. Remember, you have n-2 degrees of freedom when you go and find that t star. And you're going to multiply it by the standard error. Now remember, this number, the standard error, it's going to be given to you. Even though there is a formula for it, you don't have to worry about it. You're always going to be given it. And then, of course, you have to interpret the value in context. So, step 1. The name of the interval is a t-interval for the slope of, so make sure you finish that off, right? Don't ever just be generic. Say, this is a t-interval for the slope of the linear regression line that is predicting the gas mileage of a car based on the weight of the car, or whatever it is. Just personalize it. Make sure it's in context. Don't be generic. The conditions, they're kind of long and not very fun, but I will say this. I'm going to go through them all now, but in a lot of times what I've seen on the AP test is I have really never seen them actually have you go through all these conditions. Oftentimes they'll say, hey, all the conditions are met. You just go ahead and worry about doing the work. So that's kind of good news. And I also see a lot of multiple choice questions where you have to find a confidence interval for slope. So in a multiple choice question, you're just looking for the correct answer. You don't have to worry about all the steps. But number one, as of course, we actually mentioned this at the end of last video, is that the scatter plot of the sample must show somewhat of a linear pattern. If you don't have a linear pattern in your scatter plot, why would you ever use a linear regression model with slope in the first place? Number two, the sample of n observations must be selected randomly to avoid bias. Number three, the sample of n observations must be less than 10% of the population from which it was drawn to assume independence. Those are pretty familiar ones. The residuals must be approximately normal with no major skewness or major outliers. And this can be done simply by checking a residual, a plot of your residuals, which really isn't that hard to do, or you'll just be given it. And lastly, the standard deviations of y does not vary with x. We want to make sure that the residual plot shows similar variability for each x value. That's kind of a weird condition that, again, I've really never seen come up a ton on the AP test. But we just have to make sure that y does not vary with x. Like these are two separate variables that we're hoping to find a relationship for. So there has to be some similar variability for each x value. And we'll talk a little bit more about that when we actually look at a residual plot, because that's where you can kind of see that. All right, so number three is, of course, the formula. I already mentioned this. This is really, really easy. You're going to take your slope, which is going to be found in one of those computer output tables. Very easy. You're going to go up and you're going to go down by your margin of error. Now remember, T star, you can use invert T on your calculator to find that. All you got to do is type in the percentage of data at the bottom. So if you're given 98% confident, you're going to type in 0.01 for that bottom 1%. That puts 98% in the middle, one at the top, one at the bottom. The degrees of freedom also have to be typed in, which remembers your sample size minus 2. And don't forget, when you take that T-star, you multiply it by standard error. That's how you get the margin of error in the back. And again, this is really, really good news because standard error is going to be given to you. So T-star, you look on your calculator, which really takes all of about 10 seconds. Standard error is going to be given to you, so those numbers aren't very difficult. So the actual finding of the interval is really, really simple. Lastly, we're going to go ahead and interpret the interval. So this is where you would say, all right, I'm 95% confident that the interval from blank to blank captures the slope of the true regression line relating the y variable to the x variable. Again, make sure that you have some context here. Don't just say, I'm 95% confident that the interval from blah, blah, blah has low slope. You got to have some context there, right? So remember, slope is trying to find a relationship between x and y. It's saying, hey, this is what we predict y to increase or decrease by for each additional x value. So make sure that when you explain that, you're understanding that, hey, I don't know what the true slope is. I only know what my sample slope is. But the true slope for x and y could be anywhere from this value to this value. And again, we'll see that in a couple of examples here. So make sure your interpretation has tons and tons of good, rich context, please. All right, now I have several examples for us to explore here. So we're going to see those in the next video, so stay tuned. That way we can kind of go through each example one by one and really see how, I really want you guys to understand that this is so easy. Like, this stuff is all given to you. You don't really have to do a whole lot of work. A lot of the information going on is really more focused on the interpretation. Do you understand what's happening? You don't really have to worry about any of these complicated formulas or things like that. Even the conditions, which are a little bit more complicated here, I get it. Really, you don't have to worry about them in most cases. They're pretty easy. But in most cases, you're just really focusing on finding that interval and interpreting it. All right, check out the examples in the next video so that way you understand.